This video provides an overview of Recommendation 5 from the Using Technology to Support Postsecondary Student Learning Practice Guide. It includes a description of the recommendation, its implementation steps, and advice related to the potential obstacles to implementing from the practice guide, as well as some accessible examples of simulation technologies. Recommendation 5 advises post-secondary instructors that there is evidence of statistically significant positive impact on academic achievement when students use simulation technologies that help them engage in complex problem solving. The practice guide outlines some key reasons that instructors would want to consider using simulation technologies that help students engage in complex problem solving. Simulation technologies can allow students deeper interaction with learning material, practice using higher order thinking skills, and opportunities to make connections among concepts. These technologies can also promote engagement, which has been shown to enhance student understanding and retention. Simulation technologies are also useful for mitigating the constraints of traditional case studies or field projects, which are commonly used in higher education as they encourage students to use skills previously learned, often require higher order thinking, and engage students in realistic scenarios where they can apply their learning. Using simulations might allow students to interact with complex problems that are geographically far away from them, or they may use the simulation to manipulate time by fast-forwarding, rewinding, compressing, or expanding timeframes. Simulations are also helpful in overcoming challenges associated with scale, making very large components smaller or very small components larger. An important first question to address when deciding to incorporate simulations to help students engage in complex problem solving is what technologies actually do to support complex problem solving. There are many formats of simulation technologies, including computer simulations, game-based learning, virtual, augmented, mixed reality environments, and artificial intelligence technologies. It is important to note that just because a piece of technology exists in one of these formats does not mean that it supports complex problem solving. The practice guide emphasizes that in order for a simulation to support this kind of problem solving, it should have one or more of the following features. It should focus on realistic and complex problems. It should allow students to take multiple approaches to solving a problem and understand the implications of their approaches. It should provide opportunities to practice newly acquired skills. It should facilitate problem-based learning. It should allow for immersive role-playing. Here it is important to note that there are many visual technologies out there that are sometimes called simulations, yet many of these do not have these essential features. For example, simple animations that do not allow for interaction or manipulation do not have the features needed to promote complex problem solving. Instructors should be critical consumers of technologies labeled as simulations and really think hard about if and how the technology supports complex problem solving. It is also essential that instructors and instructional designers first determine the goals they hope to achieve with students and then choose simulation technologies that align to both the learning content and the desired learning outcomes of the course. We'll start with the California Budget Challenge. In this simulation, users experiment with different ways to divide an actual government's budget, engaging in realistic and complex problem solving. As they grapple with the problem of balancing competing budgets, they are able to try out multiple approaches to balancing the state budget. In each case, they are able to see the outcomes of their decisions immediately and grapple with the consequences of their decisions in a way that immerses them in real-life roles. At the end of the experience, simulation users can have a more nuanced idea of the budgeting process than they would with other less tech-driven approaches to the work. Shifting to a science focus, PHET Interactive Simulations, which is part of the University of Colorado Boulder, hosts a wide variety of simulations in chemistry, biology, earth science, physics, and mathematics. The collection houses over 160 simulations, along with a host of teacher resources. A classic example from the collection is a basic states of matter simulation. This simulation is aimed for an introductory science class. It demonstrates what happens when the user heats or cools a substance and then illustrates what happens to the molecules as a result. While simple, the simulation focuses on a realistic scenario and illustrates phenomena in a way that represents the complex motions of substances at the molecular level. It allows the students to compare differences between how several sets of substances react to heating and cooling. It includes a thermometer to add nuance to changes in molecule behavior. With the right instructional support, this simulation and other PHET simulations like it can provide students with practice, can facilitate problem-based learning, and can allow for students to immerse themselves in the role of scientist or engineer. In the home visit simulation, nursing students can choose their reaction to a real-life situation and see the reactions of the participants to their choice and other feedback. This one is a branching scenario developed collaboratively by several Canadian nursing schools and is available at h5p.org, where you can also create other interactive material. The economic policy simulation aims for a more in-depth experience for the student. They are required to study the economic data provided about unnamed countries, develop an economic policy, and view the results of that policy. Students have to think through the information as in any other homework assignment, but they can see the results immediately and are encouraged to explore the effects of different economic policies. This simulation is available free from merlot.org. All of these simulations and many others are available to download off the shelf from open access resources such as PHET or Merlot. Desmos is a site that has interactive math activities, generally aimed at K-12 education, but that could easily be used to support any lower-level math student. To help us implement simulation technologies in the classroom, the practice guide outlines 5 key implementation steps. 1. Assess and decide whether a course offers the appropriate context for using technologies that simulate complex problems to promote higher-order thinking and problem-solving skills. 2. Establish the learning objectives first, and then select an activity with the right level of complexity. 3. Introduce students to expectations for the simulated learning activity and provide supports to ensure they feel comfortable in the learning environment. 4. Lead students in reflective discussion to help them evaluate their own learning. And 5. Keep an eye out for new or evolving technologies that support effective, engaging, complex problem solving. As with implementing any educational strategy or approach, there are potential obstacles. The practice guide identifies 2 common potential obstacles. The first is related to time. Simulations take time to use and discuss. It also takes time to adjust instruction to make room for them. The practice guide's advice for addressing these time constraints is to gradually incorporate simulation technologies into your teaching, for example, starting by just adding one in a course. Start with existing simulation technologies rather than develop new simulations from scratch. Assign pre-work that orients students to the simulation technology so they are ready to use the simulation in class. Or alternatively, assign students to use the simulation outside of class and save class time for discussing their experiences. The second potential obstacle is related to the open-ended nature of simulations. Students may not be accustomed to this type of learning activity, and that can pose challenges. You can support them by selecting simulated activities that offer clear guidance, instructions, and readily accessible help features, and asking students about their past experiences with simulations and providing tailored help or strategically grouping students so that less experienced students have support from more experienced peers. As you grapple with using simulations to support students in complex problem solving, consider the following questions. If you are not using simulations yet, where might they be a good fit for your students' learning goals? How might they help your students with deeper learning and engagement? How might they help you mitigate the time or location constraints of traditional field projects or case studies? If you are using simulations, how well are they meeting your learners' needs? Are they helping students have deeper interactions with your learning material, giving them practice using higher order thinking skills, and providing opportunities to make connections among concepts? Are they promoting engagement? How might you refine your use of simulation technologies? This document was prepared under Contract ED-IES-22-C-0009 by Regional Educational Laboratory Northwest, administered by WestEd. The content does not necessarily reflect the views or policies of IES or the U.S. Department of Education, nor does mention of trade names, commercial products, or organizations imply endorsement by the U.S. government.